Here we have three important terms. So first one is torsional resistance. Second one is polar section modulus. And third one is torsional stiffness. To know these parameters, I would like to go with first the equation, that is T by J is equal tau by R is equal G theta divided by L. So it's a torsion equation. It is applicable only in circular cross section. First of all, I'd like to discuss the polar section modulus. So polar section modulus, it is represented by ZP. So ZP is equal, we have a equation that is polar moment of inertia divided by R maximum. So this is called as a polar section modulus. The intention of polar section modulus is when the ZP value is more, it is having less torsion, means less twisting. Means when the body is less twisting, means it is having less shear stress, then it is having more life, means the failure condition will be less. So it is a formula. So it can be calculated for any cross section. Let you consider the hollow cross section. The outer diameter is let you consider capital D, inner diameter small d. So how the ZP is going to be? ZP is equal to polar modulus, polar moment of inertia. J is equal, it is pi by 32 into d to the power of 4. D here it is capital D to the power of 4 minus small d to the power of 4, because it is a Halley section, divided by R maximum. So R maximum here it is capital D related only. So that's why I can represent it D by 2. So finally the answer is D by 16, sorry, pi by 16. So this D you have to remove. For that one, D to the power of 4, I am going to get a common term. It is going to be taken as 1 minus D by capital D to the power of 4 bracket close whole divided by D. So it can be written as pi by 16 D cube 1 minus, here this D by small d by capital D I can consider as one constant parameter, that is K to the power of 4. K is nothing but ratio of capital D to the small d. Coming to the torsional resistance, it is also very simple that what is general procedure? General procedure is when a shaft is subjected to twisting moment, then it will producing of shear stress. This is a calculation we are going to do. But in design criteria, so tau allowable they will permit, means some permit some permitted allowable stress they will give. Based on that, the torque resisted you have to calculate. That's it. It is also same equation you are going to use. So if I write here T by J is equal to tau by R, same equation I'm going to write. But here the T, sorry, here it is capital T. The T is resisted, T resistance, torsional resistance, which you can equating as tau into J divided by R, right? So here the tau, you have to assume it as allowable. So when the tau is allowable, the T is definitely resisted. Tau TR is equal tau allowable into J by R, already we consider it as a ZP. So it is a relation you have to use. It's a torsional resistance. Next one is last thing, that is torsion stiffness. So for that one, you have to know one thing, that when a member is subjected to axial loading condition, the deformation you can write it as rho is equal to PL by A. So in this one, the P by rho you can write it as AE over L actually, but this P by rho you can consider as a stiffness. So this is called axial stiffness. But here our intention is to calculate the axial stiffness, this one. Our intention is to calculate the torsion stiffness. It is also same, but it is going to be represented with KT. So KT is written as same P by rho. Here the load is T, and the deformation in the torsion is going to be considered as the angle of this. That's it. T by T theta you can write it as torsional stiffness. So from these two relations, that is T by J is equal to G theta over L. So from this KT, you can write it as T theta is equal to Gj over L. Okay. So these are three important parameters that you have to note. So next I would like to go with the problems. So before going to discuss the problems, I would like to tell you some important things that how to draw the twisting moment diagram. Twisting moment diagram. It is very important. So let you consider the shaft. The shaft will be like this. So one end is fixed here. So here we have different points. Let you consider A. So this point is B. At end, this point is C. Let you consider this point is D. So the shaft is subjected to somewhat, here it is 500 Newton meter torque. Here it is 2000 Newton meter torque, and same here it is also. So it is somewhat, let you consider 1000 Newton meter torque. It is the torque, different torques acted on a shaft. So you have to draw the twisting moment diagram for this. So the procedure is very simple. First of all, you have to draw a zero line. It is just like a shear force diagram only. So before going to draw this diagram, you have to assume one condition that so one direction you have to consider as a positive, opposite to that one you have to consider as a negative. So if you consider this is a positive, so definitely opposite it only, just to observe this is the direction, it will be in this direction only, in this direction, just you can observe. So that's why you have to consider this is positive, this is negative, and it is also negative. So first of all, it is 500 height, and this point is C, whereas this point is B, this point is A, and this point is D. Let you consider. So C to B, we have only 500 magnitude. The height of this one is 500. It is positive. By including this one, it is 500 minus 2000. It is going to be 1500, but it is negative. So this height is going to be 1500. So up to B, it is C. Up to A, it is same. But at A, if you include this one, it is 500, extra 1000 will be there. Okay, so this total height, you can write it as 2500. And finally, it is reaches to D. So it is called twisting moment diagram. So this diagram you have to learn and you have to do while solving the problems. And one more thing you have to remember that sometimes you maybe give the power instead of a torque. So the power and torque have a relation. So the power is equal to torque into omega. So here the omega is angular velocity. It is represented by 2 pi n by 60. N is also angular velocity only. N is in RPM, whereas omega in radians per second. Omega in radians per second. So we have to convert the torque like this. And also sometimes the power is given in the manner of horsepower. So 1 horsepower is equal to 746 watts. Whereas this power T into omega, if you do, you will get the power as in watts only. But the T should be in Newton meter. You have to remember this one. So it is a calculations that you should.